So the statistician is trying to estimate an unknown parameter phi based on some data. She has available two independent estimators, y hat 1 and y hat 2. And so, for example, we said the sample mean of these estimators could be, well, it could be the sample mean, it could be anything of interest. And yeah, so we were assuming that both of these estimators are unbiased, in the sense that the expectation of every iteration of the data yields phi. Okay, so rather than having a bunch of separate estimators, the statistician wants to combine these. And the combination, one possible combination, is to sum them up, but then give them some weight of interest. And this weight is non-negative and sums to 1. And we are asked to check that this phi hat here is also unbiased. Then we're going to determine the optimal weights, and then we're going to give a simple description of what the estimator in this here is amounts to in terms of the data. Okay, so let's check whether the this estimator is unbiased. So what we have here, we have phi hat, which equals to the sum wi phi over 1 plus phi over 2, like so. And now we take the expectation both sides and applied linearity, and we can pull out these constants w1 like so. So you have the expectation of phi 1 plus phi, w2, the weight, the expectation of phi 2 like so. And we know that these by assumption, these estimators are unbiased, so these would converge to phi. So we have w1, this is equal to phi, plus w2, and this is equal to phi. And then we know that the sum of those weights should equal to 1. So this term disappears here, and we end up with phi. So indeed, we have proven that this estimator is unbiased, given that these terms are also unbiased. Okay, let's now determine the optimal weights. And not only that, we want to determine the optimal weights in terms of the variance. We'll want to express it in terms of the variance of these estimators. We're also given the information that these are known as the Fisher weights. Okay, and then there was this exercise back in chapter 5. I'm going to eventually link to it, where we've shown that the mean squared error is the variance plus bias squared. Okay, so we're going to use that information as well. All right, so let's figure out what this term is. I mean, these weights are, and yeah, and then see how this relates to the Fisher weight that we were given earlier. So first of all, let's figure out what this hint is saying. So basically, we want the expectation of the mean squared error. The mean squared error is this term here. So the mean squared error is the expectation over the or estimator minus theta, which is the target of interest. And this term, we basically we're going to decompose, and we're going to realize that it actually equals to the variance and the bias, but we also know that the bias equals to 0, and then from there on we can express this mean squared error just in terms of the variance of this estimator. And that's a useful property because we were asked to express these numbers in terms of the variance of what we're interested in. So here we're just going to just use the regular algebra of opening up the parentheses like so, when we have 2 here, obviously, theta plus theta squared. Okay, we're going to use linearity, and linearity here, and then yields the expression of squared, expectation of squared of our estimator, expectation of theta, and actually, you can do the following, just that we don't have to write this down several times. We have, I mean, this is a known constant and this is a constant, so we can pull them out. So it'll be minus 2 expectation of theta here, obviously. Expectation of theta hat, that's where all the variability is. And then the expectation over, and this is also constant, so the expectation disappears. So the expectation of a constant is just this constant itself. Okay, so like so. And now we're going to add and subtract the following. The expectation of theta squared 2 minus expectation, same thing, so we've not done anything. And we're going to see that this this is the wrong add, which should be a square out here. That's what we want. And why do we want this? Well, if we add and subtract this term here, we'll see that this and that will equal to the variance. And that's useful then, because we can now express this in terms of the variance of the estimator. Okay, so this thing here and that here is the variance. And what remains are the following terms. And this equals to the bias. And that could be realized by the bias squared, I should say. Okay, and the definition of bias is, let's write it down here to the right hand side. So the bias of theta is the expectation of our estimator minus theta, and it's unbiased, right? When these two equal, when this subtraction equals, this difference equals to 0, right? And so if we take the squared of this, we end up with this term here, right? If you multiply out these terms, we end up with what we have here. So this is indeed the bias of theta squared. Okay, that's useful. And what we also know is that we just proven up in the previous exercise here is that this estimator theta is unbiased. So whatever we take this 0 squared to, it will always be 0. So this term here then is equal to 0, and this cancels. So we end up with a mean squared error equaling basically just the variance of this estimator. And that is one important thing, because now we can express this whole thing this whole thing. Well, basically, want to find the weights in terms of this variance. So we're going to do just that here in the next step. So how do we find the weights such that, actually I'm going to just do one little thing here. I'm going to do another equality here just to make this explicit, so that theta here we know is the weight of theta hat 1, right? And we know theta 2, the weight of theta, weight 2 theta, like so. And then because they are independent, these two terms, we can pull them apart without adding a covariance term, because that will be 0, and pull out a constant, and that constant is W1 squared variance of theta 1 plus W2 squared variance of theta 2, like so. Okay, so this is useful because we were asked to express this whole thing in terms of the variance of these things, and this is what why I went 2 steps ahead here to express these terms here. Okay, so in order to find the optimal weights, we want to find the mean squared error, so it's minimized, so taking it to be as low as possible. We want to express that minimization in terms of these two weights, and we could express this in two-dimensional space because we would want to optimize over W1 and W2, but we also know that W1 W2, I mean, they equal to 1, so we can express the whole thing in just one of these weights to simplify the problem. Okay, so we can move 1 step ahead here, just basically doing some manipulation of the original problem, just to simplify it even further, so that we don't have to take the okay, so we have the variance, and actually one more thing, this I'm going to call variance of 1, variance of 2, and so we have 1 plus, and then we have 1 like so, squared variance of 2. Okay, so we have an even more compact expression of the mean squared error. Now I'm going to go ahead and take the first derivative. So we're going to minimize, and then we're going to take the partial derivative, or it's actually just the regular derivative, because we have everything expressed in just one parameter. So we take this term here, like so, and this derivative is now 2, weight 1, variance of 1, plus, here we have, oh, we've forgotten the squared, like so. So this should be, the outer derivative is 2, 1 minus 1, but we have an inner derivative, and that's minus 1, so we end up having a minus here. So let's do minus, well, actually let's just do minus 1, like so, multiplied by that, just to be very clear about what we're doing. So now we have the first derivative, and we want to find where this is as low as possible, so set equal to 0. That's the next step. I'm going to duplicate this like so, set it to 0. Okay, and so from here on, oh, and I forgot obviously the variance term here, just equal to 0. And we're going to open up the parentheses here. Okay, so we have to the left hand side 2W1 V1, and then there is a minus here, and we have 2V2 times 1, so that's just as it is. And then we have a plus 2W1V2. And this should equal to 0. Okay. Now kick the 2 and the variance to the right hand side, and left are we with the W1. We factorize it out, and we put the 2 here, and then we have the variance of 1 and the variance of 2. We delete the 2's, and left we are with the weight of 1 equaling the variance of 2. Variance like so. So it's a ratio of the two variances. And equivalently, if we would have solved for W2, we will end up with the reverse relationship. So W2 is variance of 1 here instead, and we get these two weights. Now we can ask, is this minimal? Is the basically we have to minimize the variance? Well, we can check for that by taking the second derivative, and for that we'll see that this term here will become positive for all numbers by realizing that we have a minus there and a minus there. So we end up having a positive covariance. Well, basically you'll end up with this and that, and so for all numbers it's positive. So we find the weights that make this squared error as small as possible. Okay, and so these weights can be expressed like we just did, and actually the Fisher weights they do or are expressed in the scale of W1. It's a little annoying to have the variance of 2 here, so what we're going to do is just derive rewrite this term so that's written in the numerator in terms of the variance of 1, and that could be as just basic simple algebra here. So W1 equals what we have is the variance of 2, variance of 1 plus variance of 2, and this is the same thing as if we would multiply. Let's multiply by, I'm just going to make some space here, I like to have it on the left hand side. If we multiply by the variance of 1, but we have to divide by the variance of 1. Okay, and so what we have here is that this is the same thing as 1 divided by the variance of 1, and this is the same as the variance of 1 plus the variance of 2 divided by variance of 1, variance of 2. Okay, you can just use the basic algebra manipulation in terms of the rules of division, and this whole thing then is variance of 1. We can open up so that this number is expressed with that, and we'll just write it out. Variance of 1, like so, variance of 2. Variance of 2 divided by variance of 1 times variance of 2. And so here we can remove this, remove that, and we end up with the known Fisher weights by writing it out as variance of 2 plus variance of 1. And it's just equivalent, but it's nicer to have it expressed in the variance of 1 in the numerator here. Okay, that's good. Now we found the weights. We have expressed them in different terms, and now in the last part of this exercise, we are asked to, let's see, we are asked to give a simple description of the estimator found in B in terms of the random variables x1, xn, y1 up to ym. Okay, where these terms are actually the sample mean of the data. Okay, so in terms of C here, we are take a little water here. Okay, so we have C here. We have the theta hat, which is written as W1 theta 1 and W2 theta hat 2. Okay, sorry. So we have the now, but we know what the weights are, and we know also what these thetas are. They're the mean of that random variable. So let's start out by writing out what the W1 is. Well, so that we just derived that one. I'm going to use this one actually again. So this one just was basically showing you how the Fisher weights as there is expressed in the literature relates to this term here. So that's the variance. So I'm going to jump down. So variance V1 is the variance of theta 1, and that is divided by the variance theta 1 plus variance theta 2, okay, and that times theta 1. And we're going to see here that and we have obviously this plus 1 here. I'm just going to write it out like so, because I'm going to focus on the what this variance is. And so this variance is the mean of all the random variables realized, whoops, the variance of xi going from 1 to n. So actually I'm going to just going up here just so you. So we have x1 to xn is the sample. So this estimator here is the sample mean of that one. Is the sample mean of that one. Okay, and so actually I wrote x here where it should be y, because the variance of the, looking at the variance of the second estimator, okay, and that second estimator is y. Whoops. Like so, y I. It goes to up to m, and it's also the mean of that. Okay, and this is 1 over m squared. Okay, but what we have yeah, so we have 1 divided by m squared. We have also m terms. We have m terms, y's. We have the variance of those m random variables, right? And all of them have the same variance. I'm going to set them to sigma. And actually, y and x have the same variance because of the same data. So this whole expression amounts to sigma divided by m. Okay, and it will be the same thing on the other side here. So I'm just going to copy this like so, but we have variance of, actually, so this should be variance of 2, this should be variance of 1, it should be 2, like so. And this term here, therefore, we're focusing on x, but we have n of those random variables. We have the same variance, so it will be xn. Right, and so this is also sigma n, sigma m, and sigma m. And so the whole thing, this whole thing now gives us a weight by the derivation that I give you here, going back and forth. This gives us for sigma for weight 1, we'll have n plus m times the, so we have the second, which is actually, I should just move this to the right, and here we have m n plus m. And right, so what we have now, is that we have the n divided by m, but this term here is the sample mean. So this is 1n over the random variable xi, so it's I from 1 to n, and it's the mean, so that's why we divide by n. And the same thing here, but it's going over m over the random variable y. 1 to m. Okay, and so here we do have we can remove the m's, and so we end up with, let me just remove this here, so we end up with 1 over n plus m, and the random variables, sum from xi, I to the 1 to the n, plus to the I. Well, we should actually use different indices here, so let's call this j. We're going from j equals 1 to m. And so we have related the weights and the estimator to the data at hand, how it basically crystallizes. And that is the sample mean. We have shown how to basically find that estimator, minimize it, and then also characterize it in terms of the data.